Okay, so the plan for today is to finish up a couple of problems in 7.2, adding and subtracting rational expressions, move on to 7.3, simplifying complex rational expressions, and then start 7.4, solving rational equations. Just a reminder that the Unit 2 exam is this week, so it's available from, or was available from 9 a.m. this past Monday through this coming Sunday at 11:59 p.m. And as I've mentioned a couple times in the past, I strongly recommend that you complete the exam, plan to complete the exam no later than tonight, so Thursday night. That way, if anything does go wrong, if there's a tech issue, if there's a power outage or internet outage or whatever, you have some buffer, you have a full weekday to work with. If you wait until Sunday to complete the exam, and if something goes wrong, there are just far fewer options. Uh, and the sample exam is posted. The Examity practice exam is also posted. So if you haven't taken the Examity practice exam yet, I'd strongly recommend getting on and taking that. Probably right after class. I would do that, as soon as possible, so that if the tech isn't working right, again, you still have a little bit of time to get that figured out. And the quote of the day for today is from Charlie Munger, one of the two legendary kind of heads of Berkshire Hathaway, along with Warren Buffett. And he gave a speech. It's called Psychology of Human Misjudgment, and you can find it on YouTube. It's a little over an hour long. And this quote is about 24 minutes into the speech. I don't remember exactly what the context of the speech was. I think it was maybe like an invited speech, or maybe like a commencement speech, something like that, although it's way too long for a commencement speech, but maybe it was a commencement speech that he built out into a longer discussion. But he talks about finance and economic stuff, but also just kind of general, human decision making and cognitive biases. Really an interesting, hour or so. Listen, if you have time, pop that on instead of a podcast. Can hear some of Charlie Munger's wisdom, but one of his quotes in there that's very quotable is better to add a sigma than change a theory. And this requires a little bit of explanation, but basically his point is that Berkshire Hathaway as a company has done very well year after year, over decades. And there's this idea in finance called the efficient market hypothesis that essentially says that that can't happen, that you can't beat the market on average over a long period of time. And so Charlie was saying that this Nobel laureate who, was on the team that kind of worked on this efficient market hypothesis idea, uh, every once in a while somebody would bring up Berkshire Hathaway. It's like, well, you say markets are efficient. How has Berkshire succeeded? How have they managed to beat the market over this many years, this consistently? And he would say, well, it's a 2 sigma event. And that's kind of a statistics way of saying, like, well, you know, 95% of companies that wouldn't happen with, but there's going to be some outliers. There's going to be an occasional statistical outlier just due to luck, right? Somebody wins the Powerball. Like, should you bet on winning the Powerball? Probably not, but somebody wins it occasionally and makes a bunch of money. It's just chance. And then, Berkshire would beat the market for a few more years, and they would ask the guy again, well, you still think the markets are efficient? And he'd say, well, it's a 3 sigma event. So now it's, 1 in 300 event. There's a bunch of companies out there. There's going to be a few of them and he got all the way up to 6 sigmas, which is a 6 sigma event is an absurdly rare event. Um, you know, so that's Charlie's point is, this guy would rather just explain away the evidence that's contrary to his belief that he's basically staked his career on than admit the fact that maybe his model isn't all encompassing, right? And I think that's that's a human misjudgment that we tend to see as people are much more likely to dig in their heels in light of new information that's contradictory to what they believe than to give that information an honest look. And I think that's kind of what Charlie's getting at here, is that if we have a certain worldview, a certain thought about the world, and contradictory evidence comes in, we should give it a fair look, right? And we should say, okay, maybe my model about how the world works isn't as all-encompassing as I thought it was. Okay, so I think that is all the administrative stuff I wanted to talk about. Jumping into section 7.2, adding and subtracting rational expressions. Okay, so last time we did quite a bit of work adding and subtracting rational expressions with common denominators or with like denominators, and with denominators that were pretty similar to one another. Maybe that were off by a negative sign where, say, this was a 7 minus x, and maybe this was, say, an x minus 7 in the denominator. Now we're in a situation where we have denominators that are quite unlike one another. Now, an important thing to realize is we want to make these two denominators look alike. And it might be our natural inclination to try to do something like, add some stuff on one of the denominators, say the 7 the 7 minus x. Like, could I add or I guess could I subtract off a 28 or something to turn that 7 into a negative 21? That might be somewhat of a natural inclination, but because it's kind of the easiest way to make the two denominators look alike. But the problem is that if I have, x plus 1 over 7 minus x, if I want to go ahead and subtract 28, say, from the denominator to maybe make the constant look the same, and I could do a similar process for the x's and the x squared terms. Well, I don't know what to do to the top. If I just don't do anything to the top, I've changed the denominator, my expression is no longer the same. I just have a completely new expression. That's no good. And the problem is that this divided by line, this fraction, this is a division, and subtraction is on a different level of PEMDAS, so they don't really work nicely together. So we don't want to just add or subtract stuff off of the numerator or denominator. That's not really going to be the way to go. What we need to do is we need to take a look back to, let's say, just general fractions. If I had, say, 3/5 minus 1/3, what would I do? Well, I would construct an equivalent fraction with, say, a denominator of 15. I would do that by multiplying the denominator of the 3/5 by 3. I can multiply the numerator by 3, and I have an equivalent fractions property that says these two fractions are equivalent. 3/5 equals 3 times 3 over 5 times 3. And similarly, my 1/3, I can multiply the denominator by 5, numerator by 5. My equivalent fractions property says these two are equal as well. So I can multiply a thing on the numerator denominator as long as I multiply it on the other one as well. That does not work for adding. It's not true that if I add a number to the denominator and I add the same number to the numerator, I get the same fraction. That's not true. That only works for multiplying or dividing, but mainly multiplying. And then what would I do? I'd simplify this to 9 over 15 minus 5 over 15, giving me 4 over 15. Now, what if instead of 3/5, what if I had, say, 1/6 minus 1/3? Should I just change both denominators to 6 times 3 or 18? Well, that would work. That would give me a common denominator, but it's an unnecessarily large, unnecessarily complicated common denominator. I want to find the LCD, the lowest common denominator, the smallest number that has both a factor of 6 and a factor of 3. So 6 is 2 times 3, and 3, of course, is just 3. My LCD is actually just 2 times 3 or 6. Right? 18 would work, 12 would also work, but 6 is the smallest number that works. The way I like to think about this is if I have kind of a set of structures I want to build out of Legos, I would like to be able to build a 6, I would also like to be able to build a 3, not necessarily at the same time, just in general. What would my set of Legos need to contain? What building blocks do I need so that I could build a 6? Or I could take that apart and then build a 3. I would need one block of size 2, one block of size 3. I could build a 6 from there, and I could build a 3 from there. So I could leave my 1/6 as it is, but my 1/3, converting this denominator into a 6, I need to multiply by 2. Same with the numerator, right? For the 3, what am I missing here? I was missing a 2, so I kind of put that in, so to speak. Then I get 1/6 minus 2/6 is negative 1/6. No 1 there. Okay, so that was how things worked with numerical fractions. Well, they work pretty similarly with rational expressions. I want to take my two denominators and what was the first thing I did? I took my denominators and I factored them. I factored 6 into 2 times 3. Well, 7 minus x is just 7 minus x. But x squared minus 4x minus 21, I think that'll factor into maybe x minus 7 times x plus 3. I need two numbers that multiply to negative 21 that add the negative 4, and I think this does the trick. I'm going to look for common factors. Now, I do have a little extra nuance here in that 7 minus x, we can choose to write that as negative 1 times x minus 7. I'll do that to make these match up. So to build these two denominators, the building blocks I need an x minus 7, and I need an x plus 3 building block, and I need the availability of a negative 1, I guess, but we're not going to really worry about that. We're concerned with kind of the bigger building blocks here. So what's my LCD? X minus 7 times x plus 3. So let me just copy this down. I have negative 9x minus 17 over, and then instead of writing the quadratic out like this, I'm going to write it as x minus 7 times x plus 3. This minus here, it's minus 1, it's plus a minus 1 times the fraction. That can bump down into the denominator. I think we discussed this last time to help us flip the order of the 7 minus x. Oh, plus. So I changed this minus to a plus. That negative is going to hit the denominator, turn that 7 minus x into x minus 7. My first fraction already has denominator that's the LCD. My second fraction, to make an LCD, it has the x minus 7 building block already. It needs to pick up an x plus 3. And if I do that to the bottom, I better do it to the top. And I better be really careful to multiply the entire numerator by whatever I'm multiplying by. So I don't want it to mistakenly write x plus 1 times x plus 3, or like x plus 3. That x plus 3 has to multiply the whole x plus 1. Well, now I have the sum of two rational expressions with a common denominator. I add the numerators, and I keep the same denominator. I don't add the denominators or do anything funny with the denominators. Keep the same denominator. Same way we do with numerical fractions. When we add them together, we keep the same denominator. That denominator just tells us in numerical fractions kind of like how many slices we slice each pizza into. It tells us something about the slice size. In the numerator, tells us something about the number of slices we have. When we add slices of pizza together, we don't change the slice size. So the denominator stays the same, and the numerator, negative 9x minus 17 plus, and in this step, I'm also going to multiply this out. I know that I want to combine all these terms together in the numerator and then hopefully factor again. So let's multiply out x plus 1 times x plus 3. We get x squared plus x plus 3x plus 4x plus 3. So that all came from this bit. Let me simplify. So in the numerator, I have an x squared term and 4x minus 9x minus 5x minus 17 plus 3 is minus 14. Over x minus 7 times x plus 3. And I'd like to factor this numerator. I'm looking to, just like when I would get a numerical fraction, a single fraction, I would look for common factors in numerator and denominator. I would do that, at least in theory, by getting a prime factorization for the numerator. I already have a prime factorization for the denominator, and then dividing out common factors. I do the same thing here. I see my numerator, two numbers that multiply to negative 14 and add to negative 5. That's going to be negative 7 and positive 2. And I see I do have a factor that divides out. I probably want to note my restricted values, that x cannot be 7 or negative 3. And now I'm free to divide things out. Under the constraint that x is not 7 or negative 3, I can say that that all these previous rational expressions are equal to the simpler one, x plus 2 over x plus 3. So this was a lot of steps. There were a lot of things we needed to do. But if we combine the ideas of kind of modeling the steps that we would take with numerical fractions, and if you're doing a homework problem or working on an exam or something like that, you can just write a little numerical fraction problem off to the side and, see what steps you follow there and do the same steps with the rational expression. And then we simplify things according to how rational expressions work, which we've seen in the earlier in this section and in the last section. So things are slightly more complicated. There are slightly more moving parts. Things like factoring is a little bit harder to do here than just factoring a number, but the overall strategy is the same, right? We took our initial sum or difference of rational expressions. We found a least common denominator. We converted each of the denominators, if needed, into the least common denominator using the equivalent fractions property. We then combined the fractions with the like denominator by adding or subtracting the numerators. We combined like terms in the numerator, combined like terms in the denominator. Well, I guess not in the denominator. We just left that as is. And then we looked to divide out any common factors, which meant factoring the numerator, identifying restricted values, and then dividing out common factors. Remember that it's important to have the restriction x can't be 7 here because it's implied that x cannot be 7, say, here or here or here. But that's not implied here. 7 plus 2 over 7 plus 3, 9 over 10. That's a perfectly good input and output as far as just the expression x plus 2 over x plus 3 is concerned. But that's not a perfectly good output according to this one or this one or this one, or the original one. So we have to explicitly state that restriction. Now, x can't be negative 3 is still implicitly conveyed in this ending rational expression. But it's not a bad idea to just list all the restricted values. Any questions on this one? Okay, let's look at one more. So 5 over x squared, x squared plus 8x squared minus 9 minus 4 over x squared plus 10x plus 9. So again, we look at these two. I have some are difference of rational expressions where the denominators are not the same. So I need to make the denominators the same. I do not do that by adding or subtracting stuff off the denominators because that doesn't mesh well with the division. I don't know I don't know how to change the numerator to make that denominator uh, to be able to change the denominator in that way and make the fraction equivalent. I'm looking to multiply numerator and denominator by something in the first fraction and or the second fraction. So what I have to do then is find an LCD, and to do that, I come over here. I take each of my denominators, I write out, well, the equivalent of a prime factorization in polynomials is just the factorization. And that tells me what building block, so to speak, I need. And then I add in the sense of multiplying the denominator by factors, the building blocks that I need for each denominator. So x squared plus 8x minus 9, I need two numbers to multiply to -9 that add to +8. I think that is +9 and -1. So this should factor into x plus 9x minus 1. And then for x squared plus 10x plus 9, I need two numbers that multiply to +9 and add the +10. I think that is x plus 9 times x plus 1. And so I see my LCD is going to be x plus 9. I need one of those building blocks. I need an x minus 1 building block for my x squared plus 8x minus 9. And I need an x plus 1 building block for x squared plus 10x plus 9 to build that. So this is my LCD. Okay. Jump down here a couple of spaces. I want to convert each of these fractions into an equivalent fraction with an LCD as the denominator. X squared plus 8x minus 9 is x plus 9 times x minus 1. That has these two blocks, but needs to pick up an x plus 1. So I multiply denominator by x plus 1, and I do the same to the numerator. Minus, and here I have 4. X squared plus 10x plus 9 is x plus 9 times x plus 1. This has one of those and one of those, but it needs an x minus 1. So I need x minus 1 multiplied onto the top and the bottom. I'm going to leave my denominator factored, might as well. Now I'm adding or subtracting fractions with like denominators. My denominator stays the same. I add or subtract across the top. And here, because I don't want to write the whole thing all over again, I'm going to distribute at the same time 5x plus 5 minus 4x, and then minus 4 times -1 is plus 4. And I guess I didn't equate such a big fraction line. Or this gives me 5x minus 4x is x, plus 5 plus 4 is plus 9. Over this. That's an x plus 1 there at the end. If I have a fraction like, say, 3/6, I know that this is 1/2. But how would I divide out that common factor of 3? I kind of think of my numerator as being like 3 times 1, and my denominator is 3 times 2. So I can always have an extra factor of 1 floating around if I need it. I want to be a little bit careful that I don't go through all of this work and then make a silly mistake like dividing these out and thinking that I have like 0, like 0 over something, all right? Um, so I want to be careful. Number one, I want to note that my restricted values are x cannot be -9 or plus or minus 1. And then I think of my numerator as x plus 9 multiplied by 1. I divide out my x plus 9s, and I end up with 1 over x minus 1 times x plus 1. I could leave it that way, or I might want to write this as 1 over x squared minus 1. Whatever is better for me going forward. If I'm evaluating it, probably 1 over x squared minus 1 is a little easier. But if I'm continuing to work with it with other rational expressions, keeping the denominator factored might be a little better. Any questions on that? Okay, so 7.3, simplifying complex rational expressions. I think I've also heard these called compound rational expressions, where we have kind of a numerator that has some rational expression stuff going on, as well as a denominator that has that. So where do I even start here? I have to be a little bit careful with order of operations. When I see something like this, and there's like an overall fraction line, like this one here, that's kind of my main operation. So how I would think about this is x minus 2x over x plus 3. That's my numerator, divided by my denominator, 1 over x plus 3 plus 1 over x minus 3. Okay, so as an aside, um, so we're going to kind of ignore explicitly writing out restricted values here, in part because that would require us being able to solve a rational equation, and we're not getting to that until next section. So here we're really focusing on the order of operations is really the focus. So not worrying so much about the details of restricted values. That's a detail we're going to gloss over. We're not really going to explicitly state the restricted values in this section. Okay, so I have a numerator divided by a denominator like this. And I kind of see that implicitly there are grouping symbols, say for the numerator and for the denominator. So my order of operations PEMDAS says, take the numerator, simplify that as much as you can first. We should be able to get that down to a single rational expression. Separately, take the denominator, simplify that as much as you can, get that down to a single rational expression. And then you just have the quotient of two single rational expressions. We know how to work with that from previous sections. Okay, so let me come over to the side here. We'll do this kind of in some scratch work over here. The numerator, x minus 2x over x plus 3. Well, if I have a situation like, say, 1 minus 2/3, well, I just write 1 as 3/3, right? I think of 1 as being like 1 divided by 1. Right? Or over here, I kind of think of this x as being like x divided by 1. It needs to pick up a factor of x plus 3. That's pretty clearly the LCD. And then I have x squared plus 3x minus 2x all over x plus 3. Or this is x squared and then plus x over x plus 3. And I guess I can go one step further and factor everything. This gives me x times x plus 1 over x plus 3. And I think that's about as nice as I can make this rational expression look. So this was the numerator. So that's what this turns into. Now for my denominator, what do I get? One over x plus 3 times 1 over x plus 3 plus 1 over x minus 3. My LCD, I see that x plus 3 is kind of like a building block, it's prime. And x minus 3 also kind of like its own building block. This would be like 1/2 plus 1/3. There's going to be no like cooperation, so to speak, between the two, like there was up here, where I had a shared factor between the two. My LCD is just going to be x plus 3 times x minus 3. So 1 over x plus 3, I need a factor of x minus 3. To make an equivalent fraction, I multiply it on top and bottom. And for my x minus 3, I need to pick up a factor of x plus 3 on the top and the bottom. Or this gives me x minus 3 plus x plus 3, that is 2x minus 3 plus 3 goes away, over x plus 3, x minus 3, and I think that is as simple as we can make the denominator. So our denominator is going to turn into 2x over x plus 3 times x minus 3. And we could write our restricted values now, but I'm just going to go on to the next line. Like I said, I'm going to be focusing a little bit less on that in this section. And we invert and multiply. Now I have the product of two rational expressions. I know that I just multiply across the top, multiply across the bottom. I can divide out common factors. The x's divide out and the x plus 3's divide out, leaving me with x plus 1 times x minus 3 over 2 as my simplified rational expression. I know I divided out an x plus 3 and an x, so let's just go ahead and write x not equal to 0 or -3. It was easy enough to do in this case. We don't have to worry about doing anything complicated. And I would probably just leave it like this. If you wanted to multiply it out, I think the debate about which way is the simplest form is, at this point, pretty moot. We've divided out all of the common factors, so it's, I think it's in simplest form either way. Okay, what about a problem like this one? 7 plus 2 over q minus 2, all divided by 1 over q plus 2. So again, I'll choose to write this way. And then I'll do the same thing I did before. Here my denominator is actually pretty simple, 1 over q plus 2. That's already a simplified rational expression. There's nothing really that I can do to make that any simpler. But my numerator, I can simplify that a little bit. So I know that my 7 needs to pick up a factor of q minus 2 on the bottom, as well as on the top. So I get 7 times q minus 2 plus 2 all over q minus 2 divided by 1 over q plus 2. Or my first rational expression on the left here, the numerator, I get 7q, and then minus 14 plus 2 is minus 12. Over q minus 2. And then I invert and multiply. So I get times q plus 2. And in this case, well, it doesn't look like there's anything that really divides out. I don't have any common factors between numerator and denominator. That's about the best that I can do. Okay, let's look at this one. 3 over m plus 3 over n divided by 1 over m squared minus 1 over n squared. So here I have two variables. Does that really change anything? Not qualitatively. So first I'll rewrite this as numerator divided by denominator. Let me simplify the numerator, this 3 over m plus 3 over n. I see that my denominators are m and n. Pretty clearly, my lowest common denominator is going to be m times n. I have like an m to the first power building block and an n to the first power building block. They just need to multiply together. My 3 over m needs to pick up a factor of n on the bottom and on the top. So that's 3n. My 3 over n needs to pick up a factor of m on the bottom and on the top. That's plus 3m. I'm speeding up a little bit now that we've done this process a few times. When it's a simple LCD like this, we a lot of times can just do it in our head, kind of from one line to the next. If you're not seeing where this comes from, when you go back and review your notes or rewrite your notes, maybe pop off to the side, do the LCD breakdown, and work through the details if you're not seeing where these bits come from. And similarly with the 1 over m squared minus 1 over n squared, well, I just have kind of like two m Lego bricks in one denominator and two n Lego bricks in the other. They don't mesh well. I can't borrow any m Lego bricks to make the n stuff or vice versa. My LCD is just going to be m squared, n squared. I need to have two m Lego bricks and two n Lego bricks to make my two denominators. The 1 over m squared needs to pick up an n squared on the top and bottom. So that 1 over m squared turns into an n squared over m squared n squared. I don't know why I left these as m and n. I grabbed most of these problems out of your book, and I should have picked two different letters so I could speak a little more easily. And the 1 over n squared needs to pick up a factor of m squared on the bottom and on the top. So that's m squared over n squared m squared. I think I can do a little simplification here in the numerator denominator. Let me just do that. I can factor a 3 out. 3 times n plus m over n mn. And n squared minus m squared, I mean, these are both variables, but that's still a difference of two squares. That's still n minus m, n plus m over m squared, n squared. It's like a brain teaser or tongue twister or something, all these n's and m's. And then what do I do with this division? Well, I just invert and multiply by the reciprocal. So the divided by turns into a times. You get m squared, n squared on the top, and n minus m, n plus m on the bottom. And I see I have some common factors. The n plus m divides out, and one of the factors of each of m and n goes away, so we get rid of those squares. Or we get 3 mn over n minus m. Any questions so far? All right, I think maybe we'll leave this as an exercise. Just for time's sake, because we have just over 15 minutes left, and I would like to get a start on 7-4. So take a look at, I'll give you a second to copy it down. 2 over r minus 9 divided by 1 over r plus 9 plus 3 over r squared minus 81. So maybe work through that over the weekend on your own. When we come back on Tuesday, maybe I'll highlight this in, highlight this like this. Remind myself to write out the answer. And when we come back on Tuesday, I'll give you the answer. You can check your answer and make sure it's correct. So that's my reminder that whenever I go back through this, I'll remember to write up the answer for you for next time. Okay, so moving on to 7-4, we looked at operations with rational expressions, how to add, subtract, multiply, divide them. Now we're looking at solving rational equations, where I have an equation relating to rational expressions, 2 or more rational expressions. And I did the same thing here that I did up there, which was put it on the same line as the solve word, which keeps the equation editor from making it larger. So I'll bump it off of that line so it's a little easier for you to see if you're on a smaller device. But solving rational equations, I mean, it works pretty much like solving linear equations with fractions, right? If I had, 3/4 x minus 1/3 equals 2x plus what, 1/6, something like that. If I had a linear equation like this, linear equation in one variable, but with fractional coefficients, what I do, I'd find the LCD. For 4, 3, and 6, that's going to be 12. I'd multiply both sides by 12. And so 12 times 3/4 is 9. Minus 12 over 3 is 4. 24x, 12 over 6 is 2. And now I just have a linear equation with no fractions. I would just go ahead and solve this to get x equals number, and there's my answer. I do something kind of qualitatively similar. Right, I find the LCD for, starting in step 2, I find the LCD for all the denominators, multiply by the LCD to clear the fractions. That leaves me with some kind of algebraic equation. And I find all solutions to the resulting algebraic equation. So pretty simple. Unfortunately, I do have one pretty big and substantive complication here. And the complication is this issue with restricted values. So I don't think your book calls them restricted values, but we've been calling them that. And they are a really important point. Because let's hypothetically say for this first example, this won't work out this way, but hypothetically, if I did steps 2, 3, and 4 and found solutions to the resulting algebraic equation, but when I multiplied by x, when I multiplied by the LCD, I no longer had an explicit or an implicit exclusion of x equals 0. So maybe that resulting algebraic equation has x equals 0 as a solution. Does x equals 0 solve this one? Well, no, because if I try to plug in x equals 0, it blows up, right? I'm dividing by 0. So I have this extra issue of restricted values. So the very first thing I do is find all restricted values. I go through my entire rational expression, or rational equation, all of my rational expressions, and I find all restricted values first before I do anything. Then I can clear denominators. Then I can like multiply through by an x or whatever I need to do and find all solutions. And then I have to do two things in step 5. Number one, so this process of multiplying by the LCD, because the LCD now contains variables, that could introduce something called extraneous solutions. So this algebraic equation could have solutions that are not solutions to the original rational equation. Those are often called extraneous solutions. These are extra solutions that got added into the mix because of this operation here. The way we check for extraneous solutions, well, we do two things. Number one, if we see a step 4 solution, a solution to the algebraic equation that's a restricted value, we can immediately throw it out because we know that being a restricted value, if we try to plug it into the original rational equation, something would be divided by 0, something is going to blow up. We can get rid of those right away. We don't have to do anything further with them. We just, that's a restricted value, throw it out. It cannot be a solution. And of the remaining solutions, I have some other solutions possibly from step 4 remaining that I think might be solutions that are not restricted values. I want to plug those back into the original equation and just make sure that they satisfy the original equation. If I had missed any restricted values, or if I just made a algebra misstep somewhere, I should catch that if I check all of my results carefully. As kind of a side note, we see a similar thing happen when we start dealing with equations with square roots. When we square both sides, well, because -1 squared equals +1, if we're in a situation where I would hypothetically be saying -1 equals 1, that's not a true statement. But if I square both sides, then I'd have -1 squared equals 1 squared. Well, that is a true statement. I can introduce extraneous solutions in that situation as well. So this idea of introducing extraneous solutions through a more complicated equation solving step is one that that comes up in more places than just rational equations. So I have to be a little extra careful here. It's not quite as simple as solving a linear equation where we're only multiplying by numbers, so we don't introduce any extraneous solutions. We could here. Okay, so first, I'll find all restricted values, and I see the only restricted value I have is x equals 0, or say x not equal to 0. Second, well, let's find the LCD. The only denominators I see are just x to the first power. Clearly, the LCD is just x. Third, I'll multiply by the LCD. I was going to write my x afterwards, but I think it looks a little nicer in front. I've got to distribute on this left-hand side. It's really easy to forget to distribute when we're doing this kind of multiplying by the LCD and all that. So make sure to write everything out. X times 1 is x. X times 9 over x is just a plus 9. And then these x's divide out, giving me negative 20. Now I have an algebraic equation. It might be a linear equation, maybe a quadratic equation. But I have x plus 9 equals negative 20. That's a simpler equation to solve. Step 4, I find all solutions. So that would be x equals negative 29. These are my prospective solutions. Or in this case, just one prospective solution. And I can't end here, right? I have to check against restricted values and then plug in and actually check. So, yeah, so these are my prospective solutions. These, what we're saying is that if a number is a solution to the original equation, then it will appear in this list. We're not saying the other way around. We're not saying that if a number appears in this list from step 4, then it is definitely a solution to the original equation. It's important that the if-then goes the right direction. In this case, it only goes one direction. In simpler cases like linear equations, it goes both directions. That's why those are easier. Well, that's one of the reasons why those are easier. And then 5, check. Is this a restricted value? Is that a restricted value? No, it's not. So it still is possible for it to be a solution. And then let's check. Is it true that 1 plus 9 over negative 29? Is it true that that equals negative 20 over negative 29? Well, that's true if and only if, what? 29 over 29 minus 9 over 29. Is that equal to 20 over 29? And 29 minus 9 is 20 over 29. That is equal to 20 over 29. Yes, that is true. Now I can confidently say that x equals negative 29 is indeed a solution. And I would, if I had other solutions, prospective solutions still on my list that are not restricted values, I would check each of those. And then I can say that my solution is x equals negative 29. I can now confidently say this is my solution, my one and only solution. If there was another solution going through this process, it would be included in this list. Since there's no other solutions included in this list, there can be no other solutions other than x equals negative 29. And I checked that x equals negative 29 is a solution. So it went from being a prospective solution to a verified solution. Okay. Now let's work through this one. We have a couple others that we'll get to next time. But let's work through, let's work through this problem. So step 1, find all restricted values. We'll go a little bit quickly through this. I see that y squared minus 81 is just y minus 9 times y plus 9. So my restricted values, y cannot be plus or minus 9. Very first thing I do is find my restricted values. Second, my LCD is y minus 9 times y plus 9. My y squared minus 81 factors to y minus 9 times y plus 9. We have three denominators. One is y minus 9, one is y plus 9, and one is their product. So I have kind of like a blue building block, a green building block, and then a structure made of a blue and a green building block. pretty clearly those two are the multiplied together, the LCD. Third, I multiply both sides by this, being very careful with my operations. And y squared minus 81, I'll write that as y minus 9, y plus 9. I see on the right side, actually, everything divides out. That's pretty nice. On the left side, in the first term in the brackets, the y minus 9 divides out. I keep the y plus 9. Plus, in the second term, the y plus 9 divides out. I keep the y minus 9. I'm not sure why I wrote those so spaced apart, but these are all part of the same equation. There we go. I have to admit, I love many things about OneNote. I'm always hesitant to compliment a Microsoft product. I feel like as soon as I compliment it, it's going to crash. But there are a lot of things about OneNote that I like. So now I just have a linear equation in one variable. I know how to solve this. Simplify both sides, isolate the variable term, isolate the variable. 5y plus 45 plus y minus 9 equals 18, or 6y plus 45 minus 9 is 36 is 18. And then I have 6y equals 18 minus 36 is negative 18, or y equals negative 3. This is prospective, a prospective solution. This might be a solution. Or in other words, if there is a solution to this rational equation, the only thing it could be is y equals negative 3. Is y equals negative 3 a restricted value? No, it's not. The only restricted values are plus or minus 9, not negative 3. So it is still under consideration to be a solution. Let me check. Is it true that 5 over negative 3 minus 9 plus 1 over negative 3 plus 9, is that equal to 18 over negative 3 squared is 9 minus 81? So is it true that 5 over 12 with a minus plus 1 over 6, is that equal to 18 over 81 minus 9 is 72, so that would be negative 72. 1/6 is 2/12. So is it true that negative 3/12 is that equal to negative 18 over 72? And that does look right. We can divide top and bottom by 6 in the 18 over 72, and we get 3/12. So y equals negative 3 is our verified solution. It's our one and only solution to this rational equation. And that wraps us up for today. So let me stop the recording.